Hello, my name is Nguyen and I will be explaining about a problem for chemistry honors today. To first begin, I will first explaining about balancing chemical equations, identifying the limiting reagent, calculating the mass of a particular product, calculating the heat absorbed in the reaction, calculating the temperature change and the final temperature of the argon gas, and calculating the final pressure of the argon gas. Going on to this problem, I chose endothermic and photosynthesis. The problem states a hot gas surrounds a reaction chamber and supplies the heat required for the endothermic reaction below to proceed. How many grams of glucose, C6H12O6, will be produced if 5.95 grams of CO2 and 2.35 grams of H2O react completely? Calculate the final temperature of the surrounding argon gas if its initial temperature is 500 Celsius. Calculate the final pressure of the gas if its initial pressure is 1 atmosphere, assuming that the volume remains constant. And the given equation is CO2 plus H2O is the reactants, and the products is C6H12O6 plus O2. So first, we need to balance this given equation. So how to balance this equation is that you insert the coefficients into the molecules to balance both the reactant and the product. So there should be the same amount of carbon, oxygen, and hydrogen on both sides, while I inserted 6 to CO2, H2O, and O2. To calculate the number of elements in both sides, if there is a subscript, you need to multiply it to the coefficient. And you add in all similar, you add in all of the same elements on one side together to get the total amount of that element or, that element on that side. So, if it doesn't have a subscript, then it is only one of those element. Like here, carbon has no subscripts, so it is only one carbon, and then you multiply it by 6 equals 6 carbons, and that is what I did on the left side, as you see. And after calculating that, I found out that both sides balance with 6 carbons, 18 oxygens, and 12 hydrogen. And so that is what we call a balanced equation, where both sides are balanced. So now we identify the limiting reagent. First, we need to convert carbon dioxide and water into grams to find the mole of the mole to find the mole given. So how we do that is first to look into the periodic table to find the necessary element and their atomic mass. Uh, on here, first we find the mole given for carbon dioxide. So when I look into we look into the periodic table and found the atomic mass value. So in here, after that, I added the atomic masses together. And for O2, since it is diatomic, there are 2 oxygen. After I added the masses together, I got 46.01 as the atomic mass, and atomic mass is equal to the same amount of grams. So we should get 46.01 grams of CO2, and which also equals to 1 mole of CO2. And to find the amount of mole given, we divide 5.95 grams, which is the amount of CO2 given, by the 46.01 grams of CO2, or which is also called 1 mole of CO2, and got 0.129 mole of CO2 given. Then we do the same process for H2O. I found their atomic masses and added them together to get 18.02 atomic mass of H2O, which is equal to 18.02 grams of H2O, or 1 mole of H2O. I then divided the grams of H2O given by the grams of 1 mole of H2O and got 0.13 mole of H2O given. Now, as we look into both of these values, we also must look into the ratio of these two values in the balanced equation. Okay, so as we found out that the ratio of these two reactants are 6 to 6, it is similar to as 1 to 1, and that both values should be the same. Here we saw that the CO2 amount given was lower than the H2O amount given, so CO2 is the limiting reagent. And it is missing 0.001 mole of CO2. So now going on to calculating the mass of the desired product, which is glucose or C6H12O6, we need to balance the ratio of the amount of reactants we were given and the ratio of the products. Since we have a limiting reagent of CO2, we need to shorten down the amount of H2O to make it the same with the amount of CO2 because of the 6:6 ratio. So we take off 0.001 moles of H2O. And for glucose, since it has a ratio of 6:1, 6 being from the reactants and 1 from the glucose, we must divide 0.129 by 6 to find the mole of glucose produced in the reaction. I found it that the reaction would produce 0.026 mole of glucose. And for the diatomic molecule O2 on the product side, since it has a 6:6 ratio with the reactant side as well, it is also 0.129 moles. And now we convert the moles of glucose into grams. First, we need to use a picket fence structure to easily organize our values. I chose to start off with CO2 given to find the amount of glucose produced in the reaction. So I inserted that value into the picket fence structure, then I would try to cancel off the units. I inserted the actual amount of CO2 in grams on the bottom to cancel it off, and the equal of that amount of moles on the top. I then entered the ratio of the carbon dioxide and glucose, and to tell which value goes on the bottom top, since we wanted to cancel off the mole units from the top of the picket fence structure, I inserted 6 on the bottom, which has the exact unit. As those units are cancelled off, we now need to cancel off the unit moles of glucose. Similar to the beginning of this process, I used the full amount of glucose in grams in this mole conversion, which is 1 mole of glucose, and every unit cancels off completely, except for the grams of C6H12O6 or grams of glucose, which is what we wanted. So after multiplying and dividing those values, I got 3.88 grams of C6H12O6 or that amount of glucose at the end, which is the expected amount produced if the reactants react in a reaction. So now off to finding the heat absorbed of the reaction. Since this is an endothermic reaction, that's why we should find the heat absorbed, not heat release. But since heat release is exothermic, so we need to use the heat of reaction provided on the question and multiply it by the moles of the desired product, which is the glucose. I ended up having 50.81 kilojoules as the heat absorbed. We later need to convert these kilojoules to joules. So after that, we calculate the temperature change of the argon gas. We use the equation Q equals mc delta T, or heat energy equals mass times specific heat capacity times change in temperature to do so. But we first need to modify it to make the change in temperature alone. So to do this, we divide the mass and the specific heat capacity to both sides to get the delta T alone. After that, we inserted the heat absorbed value, the mass value of argon, and the specific heat capacity value of argon into that formula, and also the heat absorbed value that we got in the previous question should be converted to joules because the specific heat capacity of argon is already in joules. And to do this, you move the decimal in 50.81 3 decimal places to the right because kilojoules is in the thousands unit. And after I worked with that formula, I got 310.2 Celsius as the change in temperature. And as the product required us to convert these temperatures to Fahrenheit and Kelvin, the Fahrenheit formula for converting Celsius into Fahrenheit is the Celsius degree times 9/5 plus 32, and the Kelvin formula is the Celsius degree plus 273.15. And so I plugged in the Celsius value that I got in the previous answer to the formula, and I got 590.36 degrees Fahrenheit. And I inserted the same Celsius temperature, and I added it with the formula. Like, I plugged in and I added it with 273.15 because it was part of the formula, and I got 583.35 Kelvin as the result. So these temperatures are all the change of temperatures of the argon gas, but they are just in different units. So now moving on to calculating the final temperature of the argon gas. Since we got the change in temperature from the previous work and the initial temperature from the question, we subtract the change in temperature from the initial temperature to find the final temperature of the reaction. And we subtract it because heat is an endothermic reaction and that heat is being taken away from the surrounding or being absorbed from the system. So if it were to be an exothermic reaction, we would have to add it instead of subtracting. So I subtracted them and I got 189.8 Celsius. And since this problem also requires a conversion of that temperature into Fahrenheit and Kelvin, we used the previous formulas in the last problem for conversion. I got 373.64 degrees Fahrenheit and 462.95 Kelvin. So lastly, we calculate the final pressure of the argon gas. We use Gay-Lussac's law, which is initial pressure divided by initial temperature is equal to the final pressure divided by the final temperature. So for the temperature, Kelvin is being used because it is the main unit that scientists use. So I inserted those values and cross-multiplied them together. So also the initial pressure is 1 atmosphere as it was given. So as just as a notice. So finally I divided 773.15 on both sides to get the final pressure alone, which is 0.59 atmospheres as the final pressure. So thank you for listening to this chemistry honors explanation walkthrough, and I hope you understand everything.